I'm Anil Kumar. We'll discuss logarithmic functions later. In this particular video, we'll kind of sketch inverse of an exponential function, right? So the question here is, sketch the graph of inverse of 2 to the power of x, and second part is, write its equation and describe the characteristics. Now we have to write equation of the inverse of 2 to the power of x and then describe its characteristics. Now it is interesting to see that we could write this as let me rewrite here. We could write y equals to 2 to the power of x. To find inverse, we can switch or swap x and y, right? So when we do that, we get x equals to 2 to the power of y. In exponential form, that is the inverse. So this is the inverse in exponential form. But truly speaking, we need to isolate y, right? We need to isolate y. Now, there is no other function which can actually isolate this. So what we do is we define a new function which is called logarithmic function. So taking logarithmic function, we write like this, taking log on both sides. Log of x equals to, when we take log, we can say log of 2y. Now, we'll learn later that if I take log to the base 2, which is same here, in that case, the right side is equals to y. And so we can write y as equals to log to the base 2 of x, right? So applying some logarithmic rules, we can get to this. But anyway, for us at this stage, let us understand that inverse of an exponential function is actually a logarithmic function, right? That is by definition, right? So inverse is a logarithmic function, which is log 2 of x, since the base is 2, right? That is the inverse of this particular function, right? So I'm writing this as an inverse of this function. Well, we'll get back to this topic. Now what I did here was, I have sketched the graph of y equals to 2 to the power of x. Now how did I sketch it? Simple as that. We just make table of values, right? So just make table of values, take some values of x and then calculate 2 to the power of x. So if I have a value like, let's say minus 2, minus 1, 0, 1 and 2, then 2 to the power of minus 2 is 1 over 4, 2 to the power of minus 1 is half, anything to the power of 0 is 1, to the power of 1 will be the base itself, and to the power of 2 is 4. So these points we can identify, actually get on the graph and then join to get this curve, correct? So starting with minus 2, that is the point 1 over 4. With minus 1, this point is half. At 0, this point is 1. At 1, we get a point at 2. At 2, we get a point at 4. So you can use these points, plot the points, connect them with a smooth curve as shown here. Clearly, if we have x as a negative large value, let me write down, let's say negative 1000 or even 100. In that case, we'll get 1 over 2 to the power of 1000, right? Which is extremely small. That approaches 0. If we have positive 1000 value, then be 2 to the power of 1000, which approaches positive infinity. So that is going to positive infinity, and this is approaching 0. So that gives us the end behavior. So this gives us end behavior. So as x approaches negative infinity, y approaches 0. And when x approaches positive infinity, y approaches infinity. Now these are the characteristics of the exponential function 2 to the power of x. Now how does that help to sketch the graph of inverse? Well, it really helps. How? Let me show you. Inverse is switching x and y points, right? So if I have to find inverse of a function, then I just swap the points, right? So I write these points on the left side, these on the right side. So I say 1 over 4 should correspond to minus 2, half should go to minus 1, 1 to 0, 2 to 1, and 4 to 2, right? That is what it means, right? Inverse means swap x and y. So basically at this stage, what have we done? We have swapped x and y to find the inverse, to get f inverse of x. You get an idea, right? If I plot these points, that is x value of 1 over 4, it is minus 2. So minus 2 is at quarter, right? So here, at half it is minus 1. So half of x value gives me minus 1, okay? And at 1, it is 0, okay? At 2, it is 1, that's the point. At 4, it is 2. At 4, it is 2. Those are the points. Another thing which we are learning here is that if x is going to minus infinity, y approaches 0, right? So we are saying that when you swap x and y, so we say that when x is going to 0, when x is going to 0, y is going to negative infinity, right? So we write here, when x approaches 0, y approaches negative infinity. Similarly here, we can say when x approaches infinity, y approaches infinity, right? We just swap these, right? So when you swap these points, that means you're doing interchange x with y. This is what you get. So basically, what you're saying here is that as the x value becomes closer and closer to 0, y becomes negative infinity. Do you see that? And as x approaches large value, the y also increases, right? Y also increases. So combining these, we can actually sketch the graph. So this graph for us will be kind of like this. Do you see that? Okay, that should go through this. So that is the graph for log to the base 2 of x. And this is inverse of our function, and that is what logarithmic function is. So whatever graph we are showing here, we call that as log to the base 2 of x. You get an idea, right? So this is a new function for us, and that is how we treat it. And clearly what we see here is that if I kind of sketch a line which is going midway, for example like this, right? Then you will notice that this line, which is y equals to x, forms a mirror where all these points are reflected. So it works perfectly fine with the definition of inverse which we have learned so far, right? So we know that the inverse of 2 to the power of x is log to the base 2 of x, correct? And that's the graph of this. Now coming back to the characteristics of this inverse, which is logarithmic function for us. So from now onwards, we'll just call it logarithmic function, okay, to the base 2. Since the base is 2 for exponential function, we'll keep the same base for the logarithmic also. So what we find here is that the domain is x belongs to real numbers. As you can see, x should be greater than 0, right? As far as the range is concerned, range is y belongs to real numbers, all right? So you can clearly see that the domain and range also swaps. So here, the domain is all real numbers. Here, range is all real numbers. Range is greater than 0, domain is greater than 0. So that is perfectly fine for us. And then you can always see that the logarithmic function will have x-intercept at x equals to 1. It is always increasing, and there are so many other characteristics which you can write down. So it is always increasing, and it will never have any y-intercept, the base function, and the x-intercept is always at 1, correct? So these are different characteristics which you could list while describing this logarithmic function. I hope that helps. The idea for this video was to introduce you to logarithmic functions and link it with exponential functions. You know, logarithmic functions are inverse of exponential functions, and that is how we could actually generate them even without knowing anything about them, right? Reflecting exponential function on line y equals to x, swapping x and y coordinates, we can sketch and then also describe the graph of those functions. I'm Anil Kumar, and I hope this helps you to some extent. You can always subscribe my videos to learn. Thank you and all the best.